All right. Hello and welcome, everyone. Liz, would you like to introduce our speaker for this afternoon?
Yeah, so we have not just one, but a whole variety of speakers today. So I'm excited. I think the first person we're going to be hearing from is Josh Semeter, who is a professor at Boston University and the lead author of the brand new Steve paper that just came out, along with many of the co-authors. I think all of the co-authors are on this call. So Michael Hunnekuhl from Germany, who did a lot of the citizen science, a lot of analysis for this paper. Michael Hirsch, who's from Boston University as well. And I think you're the one other person I haven't met who's not a citizen scientist. And then in the amazing photographer realm, we have Neil Zeller, Alexei Chernenkov, if I have pronounced your name correctly-ish, hopefully. And
Jun is not able to join us today.
Jun is not able to join us.
But Jun Wang was the last author.
Yeah, thanks. So yeah, Josh, do you want to kick us off here?
Yeah, so I don't know if we're coordinated across several speakers. I just know about Michael.
So
hopefully the timing will work out okay. If we start to blabber on too long, let us know. Michael, I'm gonna say brief words about your work, which has gotten a lot of attention, also in the commentary for the paper, and then I'll hand it off to you at the end to discuss it in some more detail, and tell the citizen scientists how to do even better next time. But it's really, yeah, so it's an amazing piece of forensics he did, and we have done a lot of inferential work based on these beautiful images. I'm going to go ahead and let's see, share my screen, I hope. Let's try to see if this will work. How about this one? Okay, I'm assuming that's showing up okay.
Yes, thank you so much.
Yeah, and Laura and everyone, thank you so much for having me. Some of these slides come from some technical presentations, but this will definitely be accessible to everybody. But I will ask you to think about some basic physics and you know, kind of algebraic approach into the physics, because it's useful for everybody to have an idea of what's going on up there physically, I think. And so here are all the co-authors on the paper. I hope I didn't leave any out. This paper was just a dream come true, because it's, you know, my whole life I've wanted to figure out a way to work at the nexus of art and science. And this is like the poster child of that. And, you know, this image here, which whose credit I wasn't able to find, is a terrific example. One of the fun things about Steve is that it looks like Aurora, but it looks a little different than Aurora. And when one who is experienced with looking at the Aurora looks at an image like this for a few minutes, it should become clear that there are some serious distinctions. And sometimes when there's a distinction from another phenomenon, sometimes it's just a tweak. And other times you're looking at something that whose resemblance is just coincidental in some sense to the phenomenon you know. And it seems as though every time we look closer into Steve, we find something that just doesn't fit our experience or prior biases very well. So this is from Edwina Podemsky. Don't know if anybody knows her, but some terrific Steve images have appeared through her work online. I love this one because it highlights almost everything that we want to think about with this phenomenon. I guess, let's see, do I have a cursor on here? Oh, I guess maybe I'm not going to have a cursor. All right, that's a little bit of a bummer. But the, let's see, is there a way to turn that on easily? No, probably not. All right, anyway, we see the purple kind of whitish gray colored stuff above. We see that it actually has two different colors in this image. One sort of towards the upper right looks a little more purplish than the stuff that's looks like it might be nearer the green stuff. This is an issue that we're thinking about carefully right now. This might bear some, the phenomenon might have some relationship to stable auroral red arcs, which is a kind of an ancient feature identified back in the 50s. And the green features look remarkably similar in some ways to green line features we see in the aurora, but in other ways it doesn't quite match that model. The supposed field aligned structures have some twisty nature to them that don't exactly paint out the magnetic field, which is what we would expect. And what we decided to focus on in this paper were the little green streaks you see below, which are in entirely the wrong orientation and so forth. And the paper does not reach any solid conclusions yet about what these are, but attempts to put some quantitative constraints on it.
Josh, I'm
Yeah.
not sure I'm seeing are you on the second slide now, or on
Yeah,
the first slide? I'm not, yeah.
I'm still seeing the title slide.
Oh,
Yeah.
thank you very much. Let's do a different thing then. Wait a second.
I guess just for clarity, by wrong orientation, like wrong in terms of not geomagnetically aligned.
Yeah, that's what I mean. Thank you for pointing that out. I'm just going to share my desktop, and hopefully that'll be something that'll solve this problem.
Now we can see your cursor as well.
Yeah. Okay. Damn, I thought I was good at Zoom. How about, do you see, let's see, this is the title slide. Do you see this?
Yep, and then flip to the dip. Now we see the next slide. Edwina.
Yes.
Podemski.
Okay, thanks very much. All
Love
right. I'm so glad, Elizabeth, you stopped me, because sometimes you don't know when to stop the speaker because you're not sure if they're talking about something that you're just not seeing. But to recap here, that we've got all the different kinds of Steve phenomenon that we're interested in, all kind of captured in a single image. And the focus of this paper was on the little streaks that appear apparently below, but also it should be stated that it's really easy to get fooled by projection effects in looking at the aurora, and in particular this phenomenon, which is at a lower latitude and the field lines are inclined differently and so forth. Okay. All right, we should be moving on to a schematic right now. And the main thing I want to mention, the biggest possible picture one could think about is that, you know, we are the result of living within a low entropy system. We have a sun, we have a planet. The sun is expelling its extended atmosphere into our environment. It's a plasma, so it interacts with our own magnetic field in ways that we're still trying to understand. It's a heavy focus of NASA research. And one of the things that happens is there's a connection of the solar wind magnetic field into our own magnetic field. The kind of laws of electromagnetics tell us that means we're actually adding energy into our system. And that energy's got to go somewhere. Everybody who's interested in studying the aurora should bear in mind that you know, what the auroral zone is essentially a huge kind of global sized lens of all of this physics that's happening between the solar wind and the magnetosphere. All right. And so people do things like this. They develop schematics to try and map what's going on in the magnetosphere right down into the auroral zone. And I won't describe this figure in detail, but suffice it to say that Steve is yet another manifestation of you know, how the sky reveals what's happening in the magnetosphere by virtue of photometric emissions, by virtue of optical signatures. And in this case, its optical signatures are quite a bit different than those associated with standard aurora. So one thing one might be interested in doing when looking at Steve is to compare it to auroral phenomenon and see what's the same and what's different. And so in the upper left is a Steve image, and the other three images are images of the aurora. If we go sort of counterclockwise, in the lower left is a nice view, a nice still from a geomagnetic storm. And when the geomagnetic activity is quiet, we go to the left of that and we get these quiet arcs. And I would mention that even those boring, if you will, quiet arcs are not understood, and this is a major outstanding problem in magnetosphere-ionosphere coupling. And then in the upper right are images near the boundary of the auroral oval, the poleward boundary, where we get particles that are accelerated by special plasma waves called alphane waves. And they produce these beautiful long rayed structures that change color as they go upward in altitude. And these also bear some relationship to Steve. And it can be forgiven to think that the people who thought it was the same phenomenon should be forgiven. One of them, the major findings from 2019 was that the spectrum of Steve doesn't make sense. It's not reconcilable with the spectrum in the upper right corner. We know what should happen when we shoot electrons into the atmosphere. We should produce a very particular fingerprint in the optical spectrum. And that fingerprint doesn't exist in Steve. So looking in the upper left, the green stuff in a nutshell is too green. It's essentially pure oxygen 5577 emission. You can't penetrate an electron to that altitude without also producing other emissions. That's the basic conundrum. The red emission is not pure red as in the oxygen 630 nanometer emission, but rather it's a continuum emission. It has contributions across most of the visible spectrum. So the spectrum is all wrong for being purely produced by precipitation, even if it does play a role. And so let's go to the tape. So this is one of the beautiful movies provided by Alexei Chudenkov, which got us originally thinking about this work. If you haven't seen these things before, so this is played at probably 20 frames per second. I don't remember exactly, but it's recorded at, if I recall, 4-second cadence. So this is a time lapse. And what we're interested in is the green stuff to the left, and not just the sort of field line looking green stuff, but also the small streaks. And you can see an airplane flying through that was petrified running into Steve and needed to take a quick corner. So that's a real space weather effect. Anyway, okay, so let's go and let's spend about 2 minutes just trying to figure out what's actually happening up there. How do we get emissions like that, equatorward of the auroral oval, with such incredible intense structure in multiple wavelengths? All right, and it's actually not too surprising that it should be there once one looks at the ionosphere. What you're looking at here in the top is a map of the ionosphere produced from GPS receivers located across the entire planet. So what they measure is the total integrated plasma above you, all right? And based on the receiver geometry that we have, obviously you can look at this image and realize we have lots of receivers over the United States. We have very few over Africa or over the oceans. You get these kind of features. I'm going to play the movie through a little bit here. The features that are kind of walking around correspond to just when the satellites come into the field of view. And what you'll see forming in the blue up top, I'm going to kind of stop the movie somewhere around now. And the feature here is what we call the main ionospheric trough. But it should be remarkable. It's always remarkable to me that it appears as such a coherent reduction in the plasma density across the entire continental United States in this case, and penetrating down, as you can see, over Calgary. So this is exactly the environment under which the Alexei's movies were taken. This is, in fact, the same event. This is 2000, oh, maybe I put the wrong one in. Well, anyway, it's a very similar event if it's not the exact one, all right? And so this is the context within which Steve forms, all right? And you've heard probably in other talks from other people that there are these supersonic plasma jets flowing in this region. Where do those plasma jets get their velocity? Well, we have a stable magnetic field in the Earth. All you have to do is apply an electric field transverse to that magnetic field, and you're going to get the plasma moving. This is a well-known Hall effect. And so the velocity in the plasma is essentially equal to the electric field over the magnetic field. So then what happens next? How do we get velocities that could become unstably large? Well, that electric field, okay, the electric field is equal to the current over the conductivity, the electrical current over the conductivity. The relationship between these parameters is shown quite nicely here. If you put a current into a conductive medium, it's going to cause it some energy to dissipate exactly like putting wires in a battery connected to a light bulb, all right? And the Hall effect is this velocity vector here that's going to flow in response to the electric field across the filament, if you will, of the light bulb. All right, so that's all well and good. That means that if I increase the current, I increase the electric field. If I increase the electric field, I increase the velocity. Once you get that electric field large enough, once you get the velocity large enough, chemistry takes over and starts eating away the ionosphere. And that's what's forming this beautiful trough here, in part. When that ionosphere gets eaten away, the conductivity goes down. When the conductivity goes down, the electric field has to go up. When the electric field goes up, the velocity goes up. So this is the basic kind of feedback cycle that's leading us to sort of 8,000 kilometer per second, 8,000 meter per second velocities that are producing the light of Steve, okay? Okay, so we could come back to that if you have any questions. This is figure 1 from the paper, just showing the variety of phenomena that show these little streaks that we're trying to understand. The bottom line is that we have superthermal electrons up there. They're doing things that, they're going through turbulent processes that we don't normally see in this ion drift channel. And that's because the velocities have exceeded a certain threshold, or at least that's what we think. Okay, let's see. So if we go back to these images, what's the first thing we tried to do? Well, we said, let's look at sequences of images and see how this thing moves, and it tends to move from the poleward side of Steve towards Steve. So Alexei's images provided us a great time sequence that would allow us to track the trajectory of the thing. Furthermore, these images were fortuitously recorded by Jun Wang from another location in an imperfect but highly valuable triangulation geometry. Okay, so we can actually say something about the altitude of these features. And again, I'm going to leave that to Michael to cover at the tail end of my talk here. Another group of images that we tried to reconcile when we were putting this paper together were recorded by Neil Zeller. And this is one view of the data he recorded. The beautiful clouds for reference, but still they somehow seem to disappear, or at least they become a little more translucent in the zenith. And you'll see those green features tracking through. So this is this particular image I think was 15-second cadence and a time lapse. Okay, so we have these kind of unusual orientations. I think a lot of auroral observers have a little bit of a hard time understanding how to think about these images. What's the orientation of these features? It's really difficult to determine. They seem to be jutting out from the side or at an angle that's unfamiliar to us. They seem to contain structures that are kind of, in some cases, elongated along the feature. In other cases, they're oriented differently. Neil actually had a second camera recording this same event at a 3.5-second cadence with a little bit higher dynamic range. And so we started looking at these things in detail. Now, we didn't have stereographic images, so we had to use the star field to try and calibrate where we were looking at these things and make certain assumptions to do some analysis. So we were able to figure out the elevation and azimuth to all these features. For those who like trigonometry, the only unknown parameter, once you figure out the theta and the phi in a 3-dimensional coordinate system, is the altitude z. So one thing we can do is assume that we have a certain altitude and then do our analysis from there. So if you flip through the paper, you'll find a figure that goes from that one to this one. All we're doing is tipping these images up on end and stacking up a few samples side by side. One of the reasons we wanted to include this figure in the paper was because we're focusing on one feature that seems to be very repeatable. It felt like the best we can do at the time. In reality, we have an amazing diversity of structures in this green field of emissions, none of which are easy to reconcile with our understanding of auroral precipitation. And so clearly there will be future work coming out, certainly not just by our group, but also others that are going to attempt to explain these phenomena. All right, so what we were focusing on, this thing we call the streaks, we feel that this is exactly the same phenomenon as shown in the lower right there, this in the dashed box, where we could track this feature from frame to frame. Now, I've spent most of my career trying to find things in the aurora that are very small scale and trying to think about how to explain them. Under the premise that when you explain the smallest scales, sometimes the larger scales come into focus. So why is this little feature in the oval circle interesting? Well, it's the smallest scale feature in this image set, and it rivals the smallest scale thing we've ever seen, even in the aurora, whether it's aurora, air glow, sky glow. The natural optical emissions in the outer atmosphere don't really get any smaller than this, about 300 meters or so in cross section. It's forming always underneath other structures. It actually exists. It tracks from frame to frame over 20 seconds or more. And that's useful because it allows us to try and deconvolve some things about its motion. So one question one could obviously ask is this motion blur? If this feature is moving like the star field down here in the lower part of the image, stars are point sources in our cameras. If we leave the shutter open long enough, they start to look like streaks. Is that what explains this? Is what we tried to figure out first. All right. How might we do that? Well, we could take in the upper rightmost panel there, we draw an arrow where that streak exists in each one of those frames. We can then extract the brightness, okay, the luminosity across that arrow. We can track it from frame to frame under some reasonable assumptions of the altitude. And that's what we show in the lower right here. And indeed, what we see is that these features are separated from one another from frame to frame with a distance that's equivalent to their width. So of course, that's exactly what you would expect to see if you have a moving point source. So we feel like, at least partly, one of the limitations we need to overcome is somehow to get higher resolution measurements so that we can fully resolve this phenomenon in space and time. Right now, we have some amount of speculation based on just this motion blur issue. So hopefully that makes a little bit of sense to everybody. And then one could ask a question, well, what about the direction above? These seem to form underneath these field line structures, underneath these nice stretched out magnetic field line structures. Question, is there a connection to that magnetic field line? And so to do that, you could start doing an analysis like that by simply plotting along the red bar. So basically plotting the luminosity in the transverse direction to its motion upwards along the field line and see if anything changes as it moves through this little orbit that it's taking. Okay, and that's what you see down here in the lower left. The blue is the earliest time, and then as time progresses, we move up to the others. And we find that to the left of the feature, we start to grow a tail, and that corresponds to the upward direction. Okay, so we feel we have some evidence that there is connective tissue, if you will, from these little streaks to magnetic field line structures above. So we're starting to fill in, doing some of the forensics needed to figure out real constraints that we can put on conceptual, theoretical, and numerical models of this phenomenon. All right, and so here, this figure here is just a summary of the relationships to the magnetic field that we think we've observed from various examples. Over on the left side, panel A, that's from Alexi's images, and you can see that you kind of have this you have this motion highlighted in blue. There's a tail that develops behind the direction of motion. That's actually expected from a emission that's in this green line, because it's a metastable emission. It releases its photons slowly, so it produces a little cometary jet that appears behind it when it moves. At the same time, we're developing some connection along the magnetic field line, and we see this in the other frames as well. we see connections between field line structures in these little streaks. So this is another piece of the puzzle that we're trying to unfold here. And hopefully it was obvious that the, in this case, dark is light. We kind of put these on grayscale, displayed them as negatives so that we could better annotate these pictures. And so you can look at the discussion in the paper to see what we were thinking about this. The final thing I would mention before handing this off is that a few things to people who think about the aurora and the things you're observing. This is a nice thing to keep in the back of your mind. If you put plasma, if you inject plasma, new plasma into the ionosphere in the presence of Earth's magnetic field, it always wants to form field line structures. It'll do so naturally. It did it, there are images of the above ground nuclear tests that show artificial auroras being produced by those plasmas in a less apocalyptic mode. We've done things like release barium clouds into the ionosphere. That's what's shown here. The sort of greenish blob in this image is where they released the cloud. And as that newly created plasma evolved in time, it started forming aurora-like features. We can also make these features by heating the ionosphere. So we think a part of the puzzle with Steve is superheated electrons. We can make these kind of superheated electrons using the high altitude auroral research facility, HARP, in Alaska. And so this is a little movie here showing in oxygen 777.4 nanometer emission, auroral-like features, auroral-like features that are produced from the ground by intense microwave heating. So we shouldn't be surprised if phenomena like the stuff we're observing occurs. It's very important to know how to put the thing in space and time, in three-dimensional space and time. That is a constraint that's super important, and I believe something that the citizen scientists can really help with. It's hard. This is a phenomenon that's not easy to treat like we do other phenomena, where we're going to put cameras out, have people work stations, look into a common volume, and hope and pray that a Steve appears in that volume, okay? The mode that the Alberta auroral chasers work, as I understand it, where, kind of short warning, there might be some phenomenon appearing, let's all go out and photograph it. These types of protocols are probably what's needed to help move the science along. It's probably the only way to do it. What else do we need beyond that? Well, we need people who can do clever analytical approaches to using the data provided to us by citizen scientists. And one of those approaches was a major contribution to this paper by Michael Hunnekuhl, who figured out a very clever way to do triangulation of these features, even though we had errors in timing and very imperfect triangulation geometry. And so I'd like to give Michael a chance to describe his work to you directly a little bit, and I'll stop sharing. I presume we'll do questions all together at the end.
Yeah, that sounds great. Thank you so much. I'm really glad that both your background and analyzing all the trigonometry and the visualization of this coincided with Michael's background, and you both independently noticed these tiny little streaks, and really this paper is a result of that. Michael, do you want to share?
Okay, can you hear me?
Yes, maybe a little bit louder if you can. Yeah.
Okay, yes, I will share my screen. Just a minute. Okay, yes, thank you for giving me the chance to explain what I've done for this paper. I will give you a very brief summary of how I do the triangulation. I think there might be questions left, but yeah, I will do my best in the time I have. Okay, first of all, triangulation is not new. So there were attempts to triangulate auroras, or likely also Steve's at the beginning of the 19th century. But at that time, researchers fight with the problem that it was not possible to do coordinated observations just because there was no telephone network to coordinate observations. And the first who established coordinated aurora triangulation campaigns was the aurora pioneer Carl Stürmer, who built up a network of observation stations in Norway and started with triangulations in the early 20th century and did that for, I think, more than 14,000 cases, and found also a lot of subtypes of aurora. You can see here also a link where you if you're interested, can have a look at more historical Steve candidates. Okay, go ahead with triangulation. First challenges. The main problem if you want to do triangulation with citizen science images is that in most cases you work with timestamps on your images that might be wrong, and without further information it is in many cases difficult to define the error, and this is one of the main problem, to find ways to handle that. The problem is that most observers that do not calibrate the cameras when they go out for observation, just because this is not necessary. If you want to take a good picture, you just have to be sure that you have your battery with you, an additional battery if the first breaks, and so on. But in general, it is not very important to check the camera time. But for triangulation, it is very important because in some cases, especially if you have observers you want to combine with a very short baseline, you have to use images with a relative timing accuracy significantly better than 10 seconds, and you have to find ways to select images that fulfill these requirements. And you also have to check the absolute timing accuracy because the absolute timing and also the position of the observer have also some influence on the accuracy of the triangulation. And the solution to overcome these challenges is that you have to select observers which recorded image time series, so that you are able to search for best fitting structures, especially in case of Steve, because if you have a closer look to the picket fence structures, you see that these structures changes quite fast. So if you took photos with high cadence, you can see that even with a delay of a few seconds, there are significant changes in the structure. And you can use this structure changes as a kind of clock to combine images from different observers. And the second important thing is you must be able to identify landmarks in at least one image, to use this landmark or its position in the image and the position of stars in the background to calculate the absolute time for the image. And if you have a landmark which is far away means few 10 kilometers, you can reach accuracies of less than a minute in the absolute timing. First of all, you have to identify and find observers who potentially recorded simultaneous observation, and to do this, you have to check lots of images posted in social media, and I use mostly Facebook Aurora groups to search for such potentially simultaneous observations, and so far I was able to identify several events where it should be possible to do triangulation. At least one of the observers must have recorded a time series. That is important to optimize the matching. And of course, the faster the image cadence, the better the result is. So this requires, in general, exposure times of just a few seconds, and so short exposure times are not typically chosen by many observers just because they want to colorful, nice pictures. But there are a few observers who did that, and especially from those observers, you can use images to try triangulation. If you have identified the observers and one of them has taken an image time series, you have to identify substructures in the images that changes significantly over the time comparable to the image delay in the time series, so that you are able to find an optimized combination for images. And here's an example for such a fitting process, which I did for our paper. You can see on the left side 4 images taken by Alexei Chernenkov, separated by 4 seconds. And as you see here, there are, for example, here these. Can you see the cursor? Okay.
Yes.
You see here 2 regions of interests, and in region of interest 1, you see these 2 streaks, and these 2 streaks changes in structure over times of less than 4 seconds. So if you compare these 2 images, you see noticeable changes in the structure of these streaks, and what you have to do is that you have to find the right image that fits best to a reference image taken by another observer, and I use this image on the right side as a reference taken by Jun Wang, who also recorded the time series, but not with such a high cadence as Alexei did, and he also changes the position or the orientation of his camera. So there are a few time slots where both field of views are more or less the same, and that allows me to find a few images that can be optimized and combined. So going to the next, what is also important for the calculation is to find the absolute time of the image. The absolute time is not as important for the calculation as the relative timing accuracy, but if you would have an error of multiple minutes, that would have an influence for short baselines. What you see here is on the right side is you can see in the background here some mountains, and I was able to identify these mountains on maps which are open access provided by Open Topo Maps. And yeah, I was able to identify these 2 peaks here, and that allows me to compare the azimuth position of stars in the background with the azimuth view angle for the peaks of the mountains. And by comparing these positions, you can calculate the time offset between the camera timestamp and the correct time. And for this case, I was able to calculate an error in the range of less than 2 minutes absolute. So then next step, you have to calculate, of course, the observer distance. The observer distance on basis of the provided coordinates. You also have to check if these provided coordinates are plausible. In this specific case, we had a very demanding case because we have to work with an observer distance of less than 30 kilometers, which is challenging to do triangulation. So it is much easier to triangulate if you have a baseline of 100 kilometers or even more. So then next step, identification of reference stars in the background. I use the the freeware program Stellarium for that, and do the identification manually. It's not a very difficult task. do that if you are familiar with Starfield identifications. Then, yeah, determine azimuth and height view angles for the reference stars behind the structure you like to analyze. And next step is then that you have to calculate the on-ground distances from the observer to the projection of the structure reference point on ground. What does that mean? You have here on the image the 2 points A and B. A and B stands for the position of the observers, and the point P1 is a point directly beneath the structure you like to analyze on ground. So the structure you like to analyze is somewhere above P1, and what you need for the analysis is the distance on ground on a 3D Earth from A to P1 and B to P1. For my analysis, I approximated the Earth as a sphere, but the algorithm can easily be changed to elliptical models, but this is only necessary if you have a really, really long baseline, which is not the case for this observation. So then next, you have to calculate the height for the reference structure independently for both observers based on the on-ground distances. So this is a calculation you can do in a two-dimensional plane. This graph shows, gives you an idea how it works. So you have an observer looking at the structure. You know the distance from the observer to the point P2 directly beneath the structure, and then you can do some triangulation to calculate the height. And you do this independently with the height view angles for both observers. And if your calculation is correct and all the parameters you put inside are correct, both heights have to be the same. Otherwise, both observers do not look at the same point or look at the same point at different times. So this is a very important point to check if these two heights are identical. Otherwise, you have no idea how big is the error of your analysis. It was also
Michael?
very, yes?
Hi, I think we're going to take 2 more minutes for presentation, and then we'll take questions for the last 10 minutes of the meeting. Does that work for you?
Okay, I will speed up a little bit. Okay, then next picture you see here the two images we combine, and the challenge in our case was to find reference points in the structure you can see here on the right side. Where it's difficult to define reference stars. And what we did is that we calculate or triangulate defined reference points at the edge of the streak in one image with multiple points on a line between these two reference points, and check at what point the combination leads to identical heights for both observers, and this point, which leads to identical heights, is the correct associated point in the second images, which fits to the defined point in the right images. And this is a very important point if you want to triangulate with a very short baseline, but it only works for streak-like structures as we have in this case. And what comes out is here the diagram with the heights, and what is very important, I did mention it before, the algorithm does not calculate once for each point the height, but several thousand times with arbitrary chosen parameter sets within the error ranges for the view angles and observer positions. And this is very important to get a feeling or to get a precise number for the error of your analysis, because you see what happens if the parameter input is changed, and if you have a very short baseline, you can see that the error can be quite high. So just as a conclusion, I only want to give us suggestions for the future to ease triangulation in future, it would be very, very helpful to work with images which are calibrated in time directly before or after the observation campaign. That can, for example, be done with for some cameras with applications that check the official time, or what you can also do is just take a photo from an extremely precise clock and use this as a reference. And what would also be very helpful would be if observers coordinate their observations by phone. So call each other, say where they are, and give commands when to start an exposure, with what exposure time, and with what camera orientation relative to the stars.
Awesome.
Okay.
Thank you
That's all.
so much, Michael. There's been a lot of interest in this in the chat. I'm going to give you a chance to read that and also kind of pivot to talking to some of the photographers about their perspectives on these ideas. I'd like to call on Alexi and Neil next, and you are welcome to say whatever you like about all of this and about capturing the images. One question I have is kind of about your process and how you really push the limits to the shortest, like sub-second observations you can get with this. And that's how these tiny little streaks were found. And so that's really important as well. Yeah, I think I might, Alexi, would you be able to start? I haven't talked to you before. I'm excited to talk to you as well. And then we'll also come back to Michael Hirsch, because Michael Hunnekuhl, I think Michael Hirsch has a lot of ideas about the triangulation techniques, and you guys might want to talk more offline also.
Can you guys hear me?
Go ahead.
Can you guys hear me okay?
No, it's pretty quiet.
Yeah, hold on, sorry. Is that better?
Yeah, totally.
Well, pretty much like a lot of it it needs to be really bright, and you need to not have any moon. You need to be out there, and sorry, I'm trying to think. I'm kind of new at this stuff. I'm kind of nervous. But pretty much when you get down to like the 1 second mark, you have to sorry, I'm really nervous. I'm confused. Can Neil possibly take this?
Yeah, we can come back and give you a moment to talk, to think. I'm sorry, I'm not good on the spot. So sorry.
Hi, I'm Neil.
Go. You're all good. It's all good.
I'm nervous too. This is never easy. The biggest advantage that we've had in recent times, and why your science has been enabled, is equipment. As new equipment gets better and better, we get deeper ISOs with cleaner images, with lenses that can see further into the dark. We are able to like show these features in incredible ways. And as we go further and further, there's Aurora cams all over the world that are live, that are real time. And with Steve, it tends to be a little bit dimmer. Like Alex was just saying, that moonless night, the brighter Steve with the brightest picket fences, these green features, it ends up being those are the monumental nights that you guys are studying right now. But for my non-scientific opinion, Steve seems to always be there, and it seems like a feature that's there, and we get really dim instances of it, and just for like mere seconds sometimes, like people will report on the Chasers page, Steve, and you'll look around and you'll go, where? And then you'll shoot your camera for 30 seconds into the night sky and get just the slimmest of view. But it really comes down to the equipment these days, and the ability to get out. Like, none of us are making a living at this either, right? So this is a hobby that we're basically addicted to. This isn't a thing that normal people do. There is no glamour in this. Chris can attest to that. When we go out in the middle of the night, we are freezing. We're in our big boots. Toques are in Pennsylvania, they call them toboggans. The rest of the world are just called caps. We love it though. Like, the resulting, to be a part of this conversation is really like over the top for us that are a part of this. So yeah, to be out there and grab those images, like I say, the equipment is the key though, right? Like as things are going crazy with the details we can gather out of these night skies now, so that are beyond even eye, that we can see by eye. The 3.5 second cadence that Michael was talking about, in the images, if we can get down to like a 1 second cadence or even real time, I think that gives you all the information you're going to need, whether it's motion or what it looks like, sort of thing, right? And the equipment's the huge deal. As a professional photographer, that is my career, but I don't get paid for photographing the auroras. I host people on tours to see the aurora, so I'm probably the only one making some money at it. But we're limited in that aspect, sort of thing. There's equipment that can do it, but boy, is it expensive.
Yeah, thank you for all of those comments. The equipment and its power and also its expense is really critical. I'm
and
excited.
The ability to go out, sorry, one more thing. The ability to go out and, 2-3 hours away from city lights, the gas, the vehicles, the, everything that we do.
Yeah, yep.
I have a question.
Yeah, it's all very appreciated. Let me just say that as well. I know it doesn't put gas in the car, but go ahead, Laura.
Yeah, I was going to say, I am new to the whole photography thing. Andy is helping me catch up on that. What do you mean by cadence for those of us who are not photographers?
So the cadence is just how long that shutter is open.
Okay.
Right. So a 30-second image gathers light at a rate 1,000 times brighter than your eyes can see. If we're shooting at live, videos are photographed at 29 frames per second at 1/30th of a second. So you're getting real-time view, sort of thing, right? So the cadence, when our equipment gets better and the sensors get stronger in our cameras, the cadence that we can shoot is faster. Like we can shoot like a 1/2 second image. I've photographed live auroras in the past with the video settings on my camera. That's 1/30th of a second. Wow. For a shutter speed equivalent, right? When you're shooting 3.5 seconds cadence for these auroras and Steves, it ends up being way more than your kind of naked eye could see.
That's really cool. Thank you so much.
And it's totally awesome that the tiny little images, streaks, like, are just completely unknown. Well, not completely unknown, but like unusual, like really significant to science that they're able to be captured that way. And I also agree with you that as we have better and better, newer cameras, more photons can be seen and there are more discoveries. So that's super exciting too. Do people have burning questions? I want to also give Michael, Hirsch, or Alexi a chance to jump back on if you want, but also if people have burning questions. I'm like trying to look at you to see if you have a burning question. There's so many, there's so much.
Neil had his hand up.
Alexi, I'm going to ask you a question. What does a night look like for you when you decide to go out?
Usually is leaving Calgary and then heading northwest, probably into the mountains somewhere.
But what is that choice? What is that when you make that decision? What is your sort of factor in putting pants on, as we say?
Well, cloud cover is pretty much determines where I'm going to go first.
Yeah,
I'm willing to go like as far as Jasper or down to like Crow's Nest Pass or something.
From Calgary, which to people it's 4 or 5 hours away.
4 or 5 hours easily, yeah. But I've got a diesel car, so it really doesn't cost. It costs me 35 cents to go wherever in Alberta, so that's really not an issue. And yeah, it's just getting out there and sitting out there for hours. Like you could be sitting out there for 3-4 hours not doing anything, and all of a sudden you get 20 seconds of something, and then that's it. That's all you get to see, and then you just drive back. And
it's
like,
worth it.
It's so worth it.
Yeah.
It's one of the most exhilarating things I've seen. It's incredible.
I have probably some offline categories of questions, things about some new generations of USB 3 cameras that are for astrophotography and lucky imaging. But that would be probably comparable or even less than the price of a DSLR body, sort of the professional DSLR bodies that you have. And then just like, the feasibility of getting things like that deployed, at least a couple people. But that's more of an offline question. The second thing is, I think, is we were, just for those that weren't seeing the text chat, we were talking about incorporating low Earth orbit satellites to potentially better calibrate these images in space and/or time. some techniques that we used a few years ago. Anyway, well, those are both offline topics. Basically, we know where the LEO satellites are. So even for photos that were taken previously, even years ago, that we don't have a really good time or location calibration on, we can maybe able to make further utility of those via using known locations relatively well within certain accuracy of the LEO satellites.
Yeah, I think the newer cameras and adaptation of the Astro cameras. I know Andy's done some of that, and we've had discussions about that. So that is definitely of interest to the group, and yeah, we can definitely talk more about that, Michael. So
yeah, I was gonna say too that it's kind of one of the bigger things with newer cameras coming out is that it makes the cameras that have been out a lot cheaper. So it's to the point where there's like A7Ss and stuff are like 8 years old now or so. And I mean, I got mine for like $200. So it's kind of becoming an easier and easier thing to be able to go out and do real time. So, I mean, even with Steve, I have like 45-minute sections of it coming out here. And I feel kind of cheap compared to Canada because I can just like walk outside in the middle of the city and record it, which is really nice here in Alaska. But yeah, as far as real time goes, it's just becoming kind of more and more viable for very normal people to get their hands on cameras that can do real time. So I think that's the other side of it. It doesn't necessarily need to be the newest camera out. It's just the fact that cameras that are really, really good are getting really, really cheap, really, really quick.
Mm-hmm.
So.
That's great. And Andy's also a whiz at, fixing and modifying those cameras too. So we want to get you on here to share more about that. I'm sure that there would be a lot of interest.
Yeah.
I have another non-scientist, non-photographer question. How much detail do you think you could get on a Steve with some of the newer smartphone cameras? If I'm just out there with you can't? Okay. Because I know some of them, the night sight's picking up some of the auroras, but it's not going to pick
brightest auroras. It picks up the brightest auroras.
Okay.
Under the brightest auroras, you can take photos with anything, right? I've had my brightest aurora shooting live, focusing on the aurora. That's how bright and sharp it's been. That is so few and far between. Alaska, Andy can say that happens, more on a regular basis up there, where you get the big deep purples and the fast motions that you need live to actually shoot it well, because it just turns into a big blur. But anywhere else in the world, nope.
Thank you.
Maybe if it was a really long exposure one, that would be fun to see, but it wouldn't be quite as much of this tiny little streaks and all. But it is 10:02, and just want to say, really appreciate everyone's time here. We are going to be in touch in December and also busy doing presentations at AGU. I know several of you folks will be there, but I'm thinking maybe we could have like a virtual lunch sometime in December, casual lunch, talk about post AGU and check in a bit more. So that's the rough plan for December. And I'm happy to hang out a little bit more and keep talking, but I wanted to be mindful of people's time. And if anyone has to go back to work, actually, Chris, I know you probably have to go back to work, but you want to say hi or leave us with any thoughts before you said you had limited time. But appreciate all the presentations and perspectives. It's really so exciting.
This is really cool. Thank you all so much for being here today.
Just another third category of comment about Steve being there more frequently than we perhaps know, but very faintly. By chance, I've observed the same thing in my thesis work with a totally unrelated phenomena, highly dynamic aurora that, even a camera running at 100 hertz doesn't capture all of it. When I recorded many hundreds, maybe over 1,000 hours of that, and what I found when I came back with the machine learning algorithm is there is aurora that is there so often that if you didn't know it was there, if you were casually watching like hundreds of hour video, your eyes would fall out of your head. The other thing is when you put a machine learning algorithm on it, you can find events that are there. Like once you know they're there, they're very clearly there. And I don't know if such techniques are useful for Steve, but I would just say just analogous to those other or airglow phenomena or aeronomy phenomena that we just don't know are there because it's maybe too faint that we just haven't seen it until we knew it was there and knew to look for
Yeah, it's kind of interesting because we deal with a similar thing here with Alaska with Steve too, just because it comes out in the south sky for us. So everything that everybody shoots is always north sky, and if you turn around once in a while, there'll just be a Steve hanging out there, and no one ever realizes it. So I think
It's the
there's a
same as
lot.
us down here. We get it like our aurora are way to the north, and if you don't look east, west, or up, you never see a Steve either.
Yeah, I actually lived in central BC for a few years, and it was the same deal. It always looked like a cloud that was floating around for too long. You turn your camera and it was bright purple. I was like, oh, okay, I'm gonna shoot this now. So
Okay. I think yeah, definitely. Two things to say. One, Josh, I think I just corrected your email that you just gave in the chat. Yeah. Okay. And then two, I'm excited to get out and try and chase Aurora as well in Washington here. But you know, I'm not quite as hardy as you guys, but I haven't gotten out yet, and I've been here for a couple months, but we know there hasn't been all that much Aurora. But I'm hopeful. I'm hopeful. So
if I can just to really,
Go for
it. If people have to drop off, that's fine. I just have some camera nerd questions. Like, you know, one of the things about this streak phenomenon is I tried to get away with saying something about the relative brightness of the thing compared to something else. And the reviewer would have none of it. And they're like, you have no idea with these cameras. You don't know what they're doing at these low light levels. And so you just can't say anything about how bright it is. One solution would be to actually send you guys a standard calibration source to show your cameras so that we can do some calibration to luminosity. But in general, I'm wondering, you know, do cameras, you're not doing any automated ISO adjustment if the target gets really dim or something like that?
We're constantly changing our camera setting to gather the best beautiful view of it. Like our first goal in all of this was to catch a beautiful view of the night sky, no matter what the ISO aperture. Well, aperture is always wide open, or shutter speed was. It's, you know, down here we start at, you know, ISO 6400, 15-second shot, and f1.2. And if it turns into an event like back in May of 2017 on that one weekend, we can get to ISO 1000 1 second at f1.2 sort of thing, right? So it just varies based on what's in the sky. And our first goal is to get these things done. Magnitude of brightness, you know, some of us understand that when you're talking about satellites and Venus and that sort of thing, right? And we could estimate that, but it just looks very different in the sky. It's not pinpricks of light. It's kind of broad swaths of, most of the time it's gray to our eyes, and the camera picks up the colors.
Josh,
to be fair though, only the really wealthy of us are photographing at f1.2, Neil.
I'm not a wealthy professional photographer.
Josh,
f1.2 is pretty good.
Yeah. I was going to say that one possible, I've thought about this a little bit, and we have a student in North Dakota that most of you have probably met, Vince Ledvina, and he has a project funded with his university, and he's putting up a north-facing camera and an all-sky camera. And we've deliberately chosen one that is higher cost than the other, and trying to get some rough calibrations on those. But I think that there's possibilities of cross-calibrating different cameras from there. And so because his cameras will be running like more in the automated mode, more like the science cameras, but with equipment that's maybe more similar to what other folks have. And the intent with that is to do more science with that. So there might be possibilities there.
Mm-hmm.
It's totally fair though, comments about assessing brightness of the aurora based on the photos that we're taking, or on criticizing the brightness, because there's so many things that can go into making the aurora appear brighter or dimmer based on how you take the photo. A longer exposure, higher ISO, color, right? Like, you know, I see it all the time. One aurora evening, and you can see 20 different perspectives of that aurora that vary dramatically from the picture being nearly gray to the picture being neon green and purple, just based on photo camera settings and processing settings, right? So there's a lot that goes in there.
And personal choices.
Yeah.
Can I ask, is there a tendency to save the raw data? Or is that not something that's often done because
we all save raw data?
Yeah, I would say that is a good rule of thumb, right? So that's probably something that can be requested is in the data source effort is to request.
That might be something that I guess we
photo.
just want to discuss with the sort of the career scientists, just to be sure that we don't pester people for something we don't need. But I found in other imaging fields that having the raw image versus the buyer image was useful.
But even the raw can be affected by
shutter speed.
Right. Yes. Length, right? Yes. But it just takes out some of those unknowns.
Yeah.
So here's a thought. I thought that if you guys were interested, I know Chris would probably arrange it, and I'd be really happy to help, is to have a photographer's symposium with you scientists to get the information from us that, in a way that you'd understand as well. And we can, in that symposium, we can show you our processes, how the images start, how they finish, what they are in camera, the details and data that go along with that. So I'd be incredibly happy to share that with you.
Agreed. I agree. I like that idea.
Yeah, that's a great idea. I like that idea too.
And you're not wondering if it's real.
Most of the analysis that we've done so far has been with raw images. And so I believe, I couldn't speak for everyone on that, but I do know that that's what we try to start with, because the difference between what you said, Neil, is starting with the beauty, and like maybe you don't even want to post it publicly unless it's beautiful, but we'll take whatever it actually really looks like in raw. So that's a difference, but they're both compatible.
The imagery you're showing on these presentations are not raw images, right? Like these are processed in images that would show up. You couldn't take a raw image and place it into this presentation. So I think for the most part, you're seeing our JPEG finished images, but I have sent raws to your scientists in the past, so.
Yeah, that's fair. And I might be misspeaking for this most recent paper, but that's when I've looked at the images.
Yeah, the other hard thing is that even RAWs are like vastly different from camera to camera because of the different sensors and different spectrums that you're shooting and everything else. Like even my camera is shooting from 400 up to 700 nanometers or so because I'm shooting into the IR range on a modded camera. And having like a BSI sensor versus CMOS sensor and everything like that, you're just getting vastly different pictures, even if you sync up the settings completely. And
take that, scientist, you don't know what he's talking about.
Yeah, and even with like ISO and stuff, it's kind of a weird thing because most cameras don't change anything when you're changing ISO. It's just the camera artificially changing it because there's standard brackets. So if you're bumping up ISOs, it's not actually doing anything. It's just adding exposure time, kind of post-processing inside of the camera itself. So how your camera is post-processing when you don't know it is also a big factor when it comes to trying to determine brightness with the auroras, just because nothing is standardized at all, which is really difficult.
Sounds like there's a whole science of optics that we need to get on board with too, which is fun, like really fascinating to me.
There's entire papers written about the ISO stuff, just because there's this weird thing where if you're shooting at like 640 ISO on a BSI sensor, you're actually getting a higher dynamic range than any other ISO. So you're better off shooting at 640 and then kind of extracting it post-process as opposed to shooting a high ISO while you're out, because the camera is trying to do something that you can do better yourself. So it's
and that's a factor of the newer cameras as well, can capture that without having to do it in camera. Now, all of you understand ISO, right? This is the old ASA film, right? You used to buy 100 ASA and 400 ASA. Now we get to 6,400 and 10,000 and 256,000 ASA. So
it's an ASA.
Like Andy said, that's all just
activity of the film,
either the firmware or in post processing. When we make scientific grade instruments to record things about the aurora, we're recording just the the photoelectron events from the CCD or the CMOS sensor. we're just recording the data numbers that are digitized right at the digitization point. And that allows us to do this photometric calibration. So we can tell you how many, watts per meter per wavelength or whatever were emitted by that source. And that's the thing you need to compare to like a physical model. And I don't know, I declare ignorance on that with a standard DLSR and off the shelf and the all of these white balance and digital ISO settings and stuff like that. Amidst all that, is it still possible to just record the raw data numbers through the color mask on the chip, or is that information fundamentally lost?
Well, the hard part on that is just spectrums. So, I mean, you could be getting spectrums that are outside of it, and even if you're just recording the number of photons at a given wavelength, there's wavelengths that are going to be different than one another because everybody's shooting at different wavelengths.
Yeah, that's a great point. So we actually have models where we actually simulate the instrument function. Michael Hirsch happened to have written an entire dissertation on this. So we model the filter, we model the bare mask or whatever's on that chip, and we essentially just take the model that's producing the number of photons at a particular wavelength over a particular spectrum.
So yeah, there's going to be typically RGB. Some cameras, it's different than RGB. It's like 4 colors instead of 3, but usually it's RGB. It's like 1 red, 2 greens, and 1 blue, typically. Yeah. But there's other patterns for fancy cameras, some of which you may have.
Isn't what Andy's saying, like there's different response at the different wavelengths though as well.
Yeah.
That varies by camera.
So we have to model all that. We have to, yeah.
Yeah, and I was going to say the same thing because a lot of the cameras have built-in IR and UV filters inside of them. So they're actually shooting from like 300 or 290 up to 1100 nanometers. And then depending on the different brands, they'll have different cuts for it. So you're always getting a different kind of range of spectrums, and you can't shoot everything. Otherwise, you just end up with in focus and out of focus pictures at the same time, which is rather annoying. But
and the effects of the lens itself, which will be rather opaque and UV. And,
Yeah.
Well, what if there was a scientific equipment standardized that was next to our cameras that you could correlate like the numbers and the data beside our beautiful images?
That's what I'm talking about might be possible in the North Dakota project. Obviously, that's not where you guys are, but it can be ported. And certainly in Calgary, I would hope that there are those possibilities as well. But yeah.
Yeah, the wavelength dependence of the focus is definitely an issue. And we usually don't deal with that in the scientific grade stuff. We just, because the Aurora is a bit blobby anyway, so we just go ahead and let it go out of focus if we change the filter.
Yeah, and that is because you're taking the photographs like time lapse or automatic, like set it and forget it, right, Josh? So that's another difference between the sort of science grade like operation and the actual human operation. So it's great.
Yeah, totally.
Speaking of the human, oh, go ahead.
Go ahead. I was just going to say.
I was going to say, just speaking of the human operations, a lot of folks who watch this video may not have ever gone aurora chasing or aurora photographing before. What would you want someone watching this video who is thinking, oh, maybe aurora chasing sounds kind of cool, or maybe aurora citizen science sounds kind of cool? What would you want them to know from this experience that you've had on this paper?
Are you asking us, the photographers?
Asking everybody.
The experience is, it's not anywhere near as glamorous as what you would think, and it's not what you see online. You don't get to go out and see with your eyes what we're posting online. The cameras, gather so much more information that we're able to process and share that unless you shoot through your camera and see it through your camera, you're going to be disappointed for the most part. So your satisfaction level goes up exponentially with the amount you spend on your photography equipment.
Awesome. So managing expectations for your experience is really important. Yeah.
Yeah. Or go to Lofton, or go to Alaska, or go to Yellowknife. Go north, and then your expectations are met.
Thank you.
I would say note that half of the photographers on this call are wearing toques right now.
Is Is that a good luck charm?
Cold.
It's cold.
Cool. Yeah.
Even when you're out in the summer, which is a nice opportunity when we're this far south, it can get cold. I've been out photographing aurora in let's say early September wearing my parka because it gets cold. It can be like plus 20 during the day, but that temperature drops at night, and when you're not moving around very much, it gets cold.
One of the advantages of our latitude here in Calgary and southern Alberta is that we get aurora year round. In July, we are probably the best place in the world to catch the aurora when they come out.
Yeah.
So
Yeah,
location and
mosquitoes.
preparation are important too.
Yeah, because we get a lot of questions about that up here too. It's like, if you're gonna come to Alaska, come late in the year because we have midnight sun until midway through September. So yeah, from May until mid-September, we're pretty much off the aurora stuff. So yeah,
It's a unique
if you're planning on
experience.
going aurora tasting in the far north, yeah, you have to come after mid-September for sure.
I was going to say it's a unique experience to be fighting off mosquitoes while you're watching aurora.
But worth it, right?
Absolutely.
Sure.
Hey, I'm going to peel off the call because I have another one coming up. I just wanted to mention that. And I wanted to thank you very much for allowing me to join, discuss this stuff.
Thank you so much for coming. We really appreciate your taking the time to present to us and taking the time to talk.
Yeah.
Thank you again.
Well, thanks to all the co-authors, and you know, I've been in contact with most of you after this paper. There's so much more to think about. Michael Hunnekuhl has got a bunch of ideas. There's at least 5 or 6 PhD dissertations that could come out of the citizen science imagery that keeps pouring in.
I think everybody has a bunch of ideas who's listened to this, and the co-authors here. And I think this might be the first time we've all gotten together in person, virtually, and seeing each other. So that's nice.
Yeah.
All right. Well, thank you everyone for being with us today, and we'll definitely keep the conversation going. Have a great afternoon.